Hi everyone! This video is to walk you through the phases of Matter Lab. This is our fourth lab. You're going to need a few different things, including a stove or some type of heating unit like a hot plate. So let's get started. We're going to do a quick review as per usual, and then you get into your actual experimentation. So I am looking at the procedure that you can find on Socrates, and starting with part A, it says, share your thoughts. So in that box, we want you to either draw it on your computer, draw on a piece of paper and take a photo on your phone, scan it, however you need to, but draw some water molecules for us. So if you were to zoom in on a drop of water, what elements would you see? And how would they be arranged? Okay, now remember, when we have a drop of water, there's a lot more than just one H2O molecule. There's a lot of them. So draw a few at least, and remember our hydrogen bond chapter? Show me how they're going to be interacting with one another, okay? If you forget how we draw that, especially with the elements being involved, you can go back to the Hydrogen Bonds Make Water Amazing recording from our lecture, or you can go through and read the text from Socrates. But however you need to do it, go ahead and draw some water molecules for number one. And then number two, it's going to ask you what water is made of. So you want to answer the question, but you might also want to write down a few questions of your own that you have about water. Things that maybe you could look up online, or things that we just don't know yet. So be creative. Think of a few different things. This question is supposed to help you exercise curiosity. So not just thinking simply about what I tell you to think of for these classes, but to go a little bit beyond the topics, to be a little bit curious and to explore a little bit further. So what are you curious about with water? Maybe you're curious if there's any life that could exist without water. Maybe you're curious with how exactly water is used by the body. Okay, think of some other questions to add to number two. And then we get into part B. So part B talks about phases of matter. And of course, it says matter is made up of stuff, right? Matter makes up all of the stuff in our world. It's made up of the subatomic particles. We have different phases of matter: gas, liquid, plasma, solids. Okay, and you've just completed an ALA on this as well, so hopefully it's somewhat similar to you by this point. So make sure to read this chapter here, or this section here. It says, in this activity, we will be decomposing water or breaking it apart chemically and analyzing new combinations you've made. So we're going to be going through the phases of water. Now this lab is probably something that every single one of you has done before, just maybe not as an experiment, okay? But it's a pretty common thing to do. Now that being said, even if you think you know what's going to happen, you probably know what's going to happen. Still complete the entire process, because there are data points we're collecting along the way that are going to help you graph all of this and really see exactly what happens when water changes phases. There is a component to it that I think can be a little bit surprising for students. So again, make sure you actually run the experiment, you collect all of your data, your temperatures as accurately as you can, and let's get into it. So for this experiment, you want to remember your safety rules. We're going to be having a hot surface, whether it's your stove or a hot plate. You're going to be boiling water. So again, make sure that there aren't any kids around that could accidentally be touching things. Make sure you have a clear countertop, and make sure that you're there to watch it the entire time so you don't have water boiling over or you don't miss your data collections. All right. You won't need a ton of time to boil this, but we are starting from ice, so give yourself a good chunk of time where you can be uninterrupted and make sure you get everything done in one go. Now, as always, this is an at-home lab, but we are still pretending we are in a laboratory, so don't drink the water from your experiment or do anything like that with it. We want to try to be as concise as we would in a lab. Make sure that you pull your hair back, you wear your safety goggles, and you don't have any dangling earrings. Okay? For this, you will need your thermometer. So this was a long glass thermometer that came in your lab kit. Be careful with it, it can break. No, it's not mercury inside, but it is an alcohol, and it is still dangerous if it breaks. So use caution. You'll also need ice. You'll need a small, medium pot. I wouldn't go with anything too big. You might want an oven mitt or some kind of hot glove when you handle things. A towel would be helpful, and you'll need something to stir. So maybe a nice stirring spoon so that you can stir the water as it's going. And then of course you'll need your heat source. I think the stove is the most preferable method, but maybe you have a hot plate instead. Maybe you go camping and you use a fire. Whatever it is, make sure you have a nice consistent heat source. Okay. All right, I'm gonna jump down to my laboratory and let's get started. Okay, we are now in the laboratory, so I have all of my equipment ready to go. I have my pot that I'm gonna use. I have some ice ready to go. I do recommend, if you have the ability to get crushed ice, that might help the experiment go a little bit smoother. So you might want to give that a try. You'll need some regular cold tap water, a spoon to stir with, and then of course you're going to need your thermometer as well. So make sure that you handle this with care. It will get hot, so we also recommend having an oven mitt to actually hold the thermometer as you go, and a towel to put it on because it's going to be wet. So to get started, we're going to have the ice, add it to our pot. We have not turned on our heat source yet. And the directions say to add about 2 centimeters of water with your ice. Now you have a ruler included in your lab kit if you wanted to use it, but you might know the really quick way to tell about 1 centimeter is actually the width of your pinky. So you can use a ruler or you can kind of estimate it. Estimation is fine for this. So we want to fill the pot with about 2 centimeters of water, which isn't too much. And let's double check. A little bit more. Okay. Now once you've done that, you're always going to make sure to stir before you take your temperature. So I'm breaking up my ice, giving it a nice stir so it's all even and uniform. And now I'm going to take my thermometer, make sure that you place the colored tip in the water ice mixture, and you wait maybe about 30 seconds at least until you see your line stop moving. This temperature that you're going to record is actually for time 0. So we have not turned on the heat source, we have not started the experiment. This is just our initial measurement, how it is before we start to heat. Now your reading should be right around 0. We do want to record this in Celsius or centigrade, so make sure you're using the correct side of your thermometer for the entire experiment. And it looks like my line has stopped moving, and I am actually right around 1 degree. So again, we're just looking at where our red line stops. You might have a different color. And you can place that back on your towel. All right, safety goggles on. And then you're going to turn your heat source to a medium-high heat, whatever that looks like for you, about a medium-high heat. Now every 2 minutes, you're going to be using your thermometer to take your temperature. So I'm starting my 2-minute timer. I'm using a cell phone. If you have an actual stopwatch, that's really great too. I'm starting my timer so that exactly at 2 minutes, I will be recording my temperature. Now it says to make sure that you're actually stirring for about 10 seconds before you take the temperature. So when I notice that I'm almost at my 2-minute mark, I'm going to grab my spoon and stir. And I'm going to go ahead and take my temperature after it's all been stirred uniformly. Now you're going to record all of these numbers on your chart. And you're going to add some observations as well. So the observations that you want to have in your table are really about the phase that the water is in at that point. So my first time 0, I'll probably say that it's mostly ice and I have a little bit of water. Right? As you go, maybe you start to notice that it's turning into a lot more water, so that can be your observation. And then you might notice it's completely water, liquid water, I should say. And as you go, maybe then you start to notice some bubbling going on. So whatever you observe, go ahead and put that in your table as well. Now the length of your experiment might vary a little bit, but you want to make sure that you're getting as much data as you need to get your water to be at a boiling stage. Not just the start of a boil, but a nice solid boil for a minute or 2 before you end your temperature recordings. So your procedure says about every 2 minutes you want to take the temperature until it's at a full boil and you've completed your table. So I'm nearing my 2-minute mark. I'm going to go ahead and stir. 2 minutes, so I'm going to go ahead and record my thermometer, or record my temperature with my thermometer. Now remember, this is when we might want to start using our heat glove, just in case, because we do have a hot source nearby. And I'm going to wait until that line stops moving. And you also, when you have your thermometer in, you want to make sure it's not touching the very bottom of your pot. We want it all the way in the liquid, but you don't want it to be touching the bottom. When you do this in a lab, you usually have something called a ring stand, and that usually holds the thermometer for you, makes it a lot easier. But we don't really have one of those right now, do we? So mine has stopped moving, so I would record this temperature on my table. Okay, now I think you guys get the idea, so I'm not going to go all the way through, but I will let you guys kind of try it out on your own and collect your own data points. So make sure to get it all the way to boiling, take your last temperature, and that's when you can stop your time. Okay, so by now you should have completed your phase change experiment. Hopefully you've turned off your heat source, you've cleaned up your entire area, you've put away your glass thermometer so that it doesn't get broken on accident. You put your goggles back in their place so you can find them for next lab, and you're ready to move on. So at this point, you're going to actually graph your data. So I'm sure all of you knew the phases of water and what happens when you heat ice up for a long time. But this lab is really about seeing the data in a graph form. So you're going to take that table with all of your data points and you're going to make a graph. There's graph paper provided in the procedure if you need it. Maybe you want to draw it by hand and upload it as your homework assignment. That's fine too. But either way, you're going to use a graph. You're going to plot the data. Your time is your x-axis. So make sure you start at time 0 and you go for however long your experiment ran. You can do in minutes. That's perfectly fine. And then your y-axis is going to be temperature in degrees Celsius. And again, make sure that you have the entire range you need for the entire graph. So however hot your water got and however cold, probably starting at 0 is perfectly fine. And everything can be in the positive range quadrant, okay? So you're going to go ahead and graph your data for number 8. That's the end of the experiment then. So after you've done that, you can move on to the analysis portion. I'll go through a little bit of it with you. So the analysis, it starts out saying that all atoms and molecules are vibrating or moving. So we talked about this at the start of the course, and it's a little bit difficult to imagine sometimes, but every single piece of matter that exists on this planet is made up of subatomic particles. And those subatomic particles are constantly moving all around. We've talked about the movement of the electrons when we have chemical reactions, but even just when something is sitting there, not reacting chemically, the atoms, the particles are constantly vibrating and moving. That movement is called kinetic energy, and everything has kinetic energy. Energy of motion is another way to put it. So when a molecule is when two or more atoms are bonded together, regardless of whether or not they are the same element. So O2 is considered a molecule, but not a compound. So that might be a good definition distinction. A molecule can either be two elements or two different elements bonded together, or a bond between the exact same element, like O2 or F2 bonded together. But a compound, on the other hand, has to have multiple different elements involved. So H2O has multiple different elements, so therefore it is a compound. It's also a molecule. But those ones that just have one type of element, those are just molecules, not compounds. Little distinction there in case you didn't know that. So for water, of course, we have two hydrogen atoms bonded with an oxygen to make one water molecule or water compound. And then temperature is just a measure of how fast the atoms are moving or a measure of their kinetic energy. So for question 1, it's asking you what state of matter you viewed in this experiment had the highest kinetic energy or temperature. So what state was that water in when it had the highest kinetic energy? Okay. Make sure you answer with a state of matter. Number 2 is talking about the physical changes that water underwent. There are two physical changes that happened, okay? There's two specific words we're looking for, but you want to think about what happened to the water in the different changes it went through. You then want to fill in the temperatures that you had for your experiment for the melting point and the boiling point. So at what temperature did you see the ice melt? At what temperature did you see the water boil? Now the accepted temperature column over on the right is, of course, the temperature ranges at sea level without any impurities or other complications and variables going on. So at what temperature, degrees Celsius, do we say that water melts? And at what temperature, degrees Celsius, do we say that water boils? Your experimental temperatures might not be exactly those numbers. Again, because we're not exactly at sea level, atmosphere has something to do with the temperature of water boiling. And so your numbers might be a little bit different. But make sure to include both of those to complete the table. To answer number 4, you're giving another temperature in degrees Celsius. And then for number 5, explain why you can't get the liquid water any hotter. What happens to liquid water when it reaches 100 degrees Celsius? Now you can in fact get water to heat above 100 degrees Celsius. It is possible. But for this experiment, when it was boiling, you had an open container. It was pretty difficult to get it above 100 degrees. So write down why you think that is. And to move on to number 6. This talks about the distinction of gas and steam and water vapor. So when water reaches its gaseous phase, we actually cannot see it. When we see that steam, we're seeing something else. Okay, that's really the humidity that we're seeing, which means there has to be some drops of water in it. So just like we can't see the oxygen and nitrogen in the air that we're breathing, we cannot see water in its gaseous state. But there is liquid water in there that we're able to view, and that's why you can say you see steam. So number 6 says, of the water that you can see, what state of matter is the water rising off of the boiling water in? And suggest an explanation. Okay, now I just said you cannot see the gaseous state. So if it's not a gaseous state, what state of matter is it that you're looking at? And why would you see that? Think about it for a few minutes. It's the same reason why you go outside on a cool winter day and you breathe and you can see your breath. Why can you see that? Why does that happen? And then if you go down further, you're going to see a graph. So this is a heating curve. And heating curves exist for really any element out there. This one is specifically for water. And you'll notice it doesn't look like your graph. It looks similar, but you probably don't have those flat plateaus. Okay. This is the actual heating curve for water. And you'll notice that those flat plateaus are where certain things are happening. So number 7 says, if heat was being added from the hot plate to the water is then absorbing that heat the entire time. Why isn't the temperature rising when the water is melting or boiling? So why do those plateaus exist on the graph? Where is the energy going? Okay, if it's not actually heating and raising that graph's line, where is the energy going? And then you have a table to complete for number 8. You're simply putting in what state it's going between. So for boiling, it starts as a liquid and it goes to a gas. That is the boiling change of state. And of course, for boiling, you're going from a liquid to a gas. A gas is a higher kinetic energy state, so it takes more energy. So heat has to be added. Okay, in this example, heat is our energy source. And then number 9 is going to ask you to graph something again. So number 9 says that the melting point for mercury is negative 39 degrees Celsius. So at negative 39 degrees Celsius, mercury will begin turning into a liquid. Okay, mercury has to be very cold to be in a solid state. The boiling point for mercury is 357 degrees Celsius. So it has to be incredibly hot to be in the gaseous state for mercury. You're going to make a heating curve for mercury. It should look just like the one for water up above, so you should have plateaus for the melting point and the boiling point. And you want to make sure that you're putting the melting point at negative 39 degrees Celsius and the boiling point at 357 degrees Celsius. Okay. So you can do that graph just with the information given to you in number 9. You want to make sure to label your axes carefully. And it says you will need to start around negative 50 degrees Celsius and end around 380 degrees Celsius so that you can get all of those values in there. So draw your heating curve for mercury. Again, it's going to look very similar to the one that's given to you up above for water, just with slightly different values. And after you finish that, then you've completed the Phase of Matter lab. Great job. And of course, let me know if you have any questions.